Danica McElhenney, one of the two founding members of the Wits Cortex Club. This is December 2017, and this is the first official solo event of the Cortex Club. How are you feeling?
Excited.
Excited?
Just excited. No,
This is the second founder of the Wits Cortex Club, Dr. Tanya Calvi.
Hi.
Are you excited for today?
I'm so excited.
It's great.
Okay, thank you for your help.
Yes.
And it's going to be a successful event.
On Monday the 4th of December 2017, the Wits Cortex Club hosted their very first solo event. Before the proceedings of the day, we spoke to the founders to get some background on the club.
Okay, so I was the one that was the initiator. I had to try and sort of find somebody to share the interest, and unbeknown to me, Tanya was trying to do the same thing at the same time. So I contacted the South African Neuroscience Society as well as the MSc at Wits just to sort of find out how to go about starting a club. We needed something, there was a platform missing for where to find out about neurosciences, what's happening in it at the moment, and to sort of bring all the disciplines together, especially for a research base. And then I managed to meet Tanya through SANS, and it's how we got together and started the Cortex Club.
Obviously, so how the Wits Cortex Club came about was that Danica and I both know the chair of the UCT Cortex Club, Richard Berman. So we both chatted to him, and they were more than willing to share their knowledge and their experiences up until now. With experience from not only the UCT Cortex Club but the Oxford Cortex Club. There's also Toronto Cortex Club. So just sharing that knowledge with us. So we're hoping to stimulate interest in the neurosciences with the health sciences as well, to really bring about a change in how we treat a lot of neurological disorders in South Africa, because we do have a very specific population.
Yeah, we do, and also incorporate a student interest in it, so we can then get more people interested in research and then interested in how things happen, why they happen, where they happen, and spark interest in neuro overall.
Good afternoon, everyone. Welcome to the first solo event of the Wits Cortex Club. My name is Danica McElhenney. I'm one of the co-founders of the club. So I've had an interest in neurosciences for quite some time now, and it's actually fueled by a lecture that was given to me by Prof. Paul Mango in my second year at my BSc. I went on to do my honours in anatomy with him, and realised that there isn't really a platform which we can explore the neurosciences field across the board, all the disciplines which it has to offer. So I contacted SANS, and they really put me in contact with Dr. Tanya Calvi, who shared the same interests, and that's the Wits Cortex Club as well in February of this year. We've now since grown to include 3 more members who span various fields of research and undergraduates in health sciences, and one of which is free over here, she's going to tell you why it is that we started the Cortex Club. Thank you, and I hope you enjoy.
So the Wits Cortex Club was started as a way for starting students to explore the developments in the field of neuroscience, and it's affiliated with the Cortex Clubs at both the University of Cape Town and the University of Oxford. And the aim of the club is really to foster an interest in the different academic fields of neuroscience and to encourage interdisciplinary conversations, which are really important for the development of neuroscience.
So without further ado, I'd like to introduce Dr. David Pitcher. Dr. David Pitcher did his PhD at the University College of London, UCL, which was then followed by 2 postdoctoral fellowships at NIH in the USA, as well as MIT in the USA, and is now working as a lecturer in the School of Psychology at the University of York, studying the visual system using TMS. So thank you so much for having us, Dr. Pitcher.
So really the talk kind of breaks down into 3 main parts. TMS, or transcranial evidence stimulation. So I'll give you a background. I've used that for a long time, that's very much my area. TMS and how it's used to treat mental illness. This is the stuff I'm reading about now. So that's the middle part of the talk. That's the part which I'm going to present a series of studies not done by myself, but things that I think tell us where we are with the state of TMS and mental health research, and build that to the consensus. And then in the third part of the where I say look at the mechanism. That's where my research comes back in, is having used TMS in the healthy brain to study how the brain activity works. I think we can use that technique, I can use those techniques and hopefully convince others to use them, to study how the brain, to study the connectivity in disease specifically with mental disorders such as depression and possibly addiction, other disorders as well. So that's where the mechanisms come through. But it was really a decision, I think, by the FDA in 2008 that created sort of actually I wouldn't say a minor intuition, I'd say there's been a great interest, particularly in the US, using TMS to treat depression once it was approved. Other countries have followed, Canada, Germany, Japan, Australia, and NICE is approved in the UK as well. At the moment, depression is the only mental illness that is officially sanctioned as the TMS's treatment. Can use this. TMS is only sanctioned as treatment for mental illness. It's not sanctioned as treatment for other mental illnesses.
So, Dr. Calvi, can you tell me a bit about the Brain Matter seminars that took place in 2017, and what your vision for the future on Brain Matter seminars are?
So, How the Brain Matters colloquium was a colloquium at the end of 2016 by a few Prof. Willem Gispen from University of Utrecht, and it was hosted by the Johannesburg Institute for Advanced Studies. And me and Sahba Bisharati were students of that colloquium. And at the beginning of this year, we got speaking about how we could actually continue the knowledge that we learned. It was a three-month colloquium. So it was really bringing together a lot of students, a lot of different international experts in the neurosciences. We thought, how can we continue in a way that kind of enhances those 3 months, because it was an amazing experience. So we got together and we decided to launch the Brain Matters seminar series, which we launched in March this year, with Prof. Willem Gispen was actually the keynote speaker at that address. And then we thought that the theme for the year would be the past, present and future of neurosciences in Southern Africa. So we started with Willem Gispen. The then first seminar was Prof. Vivian Russell, who gave her seminar on the history of neuroscience in Africa. And then Prof. Paul Manga was the second seminar, which was a nice jump into the present with the evolutionary sciences, the evolutions of the 5 large brains in mammals. Then we went a bit more multidisciplinary. The next seminar was by Professor Mark Soames, looking at the neural correlates of dreaming. And then the next was Dr. Samantha Brooks from the University of Cape Town, who then addressed us on the Bayesian perspective of addiction. So it's been a nice mix of not only international researchers from obviously Europe, Southern Africa, different areas of Southern Africa, but also different topics. So obviously Sahba Bisharati is in psychology, I'm in the neurosciences, but the lectures have been at the Wits School of Public Health, and it has been sponsored, sorry I forgot the most important part, and led by the DST NRF Centre of Excellence in Human Development, and one of their drives is to kind of incorporate the neurosciences into a lot of different aspects of research. Also sponsored by the Johannesburg Institute for Advanced Studies, JIAS, and supported by the Wits Cortex Club and the Southern African Neuroscience Society. Now the final event, the final seminar will be Prof. Morten Krummelbach, who is from University of Oxford and Argus, I can never pronounce that, and he will be speaking to us about the parental brain imaging, which will be at the Nelson Mandela Children's Hospital, which is a very good venue for our final seminar, because the points, me and Saba both got a neuroimaging interest, and we were hoping to kind of initiate neuroimaging research in Gauteng specifically, because the only part of South Africa where neuroimaging research is taking place is in Cape Town. So a beautiful outcome of this year is that we have now initiated neuroimaging research with a Nyope addiction study. I'll finish scanning the last of the test group this Friday. So the Nelson Mandela Children's Hospital has been very supportive in helping us initiate that research in South Africa, and that was where the final seminar will be. So yeah, it's a lovely finale With regards to the future, we're not as sure yet. To my knowledge, this is the final seminar this Wednesday, but it's all recorded and on YouTube, and I think the target audience and the group of people that we've brought together over this year, and obviously the BITS Cortex Club and all of our activities will last for many years to come, hopefully. So it's been a very successful year.
Great, thank you very much, Dr. Colby, and
Thanks, Joe.
thank you for all your hard work put into all these seminars that is definitely benefiting students and practitioners out there, and researchers as well. So thank you.
Thanks, Joe. It's my pleasure.
But on behalf of the organising committee, I would like to welcome you all to the second official Brain Matters seminar. So we launched the seminar series in March, and we had our first seminar in April on the history of neuroscience in Africa. Now, one of the primary purposes of the seminar series is really to try and establish a network of researchers that are dedicated to advancing the field of the neurosciences, particularly in the Gauteng region, but also in South Africa as a whole. So I'm very pleased to say that in the 2 months since we have launched the seminar series, we have over 150 students and academics a part of this network. And now, thanks to Kumalani's hard work, I'm pleased to announce that we are live streaming all of these seminars, hence our...
Paul Menger is Professor in Anatomical Sciences at the University of the Witwatersrand, as all of you know. We did not meet when he was an undergraduate, but in fact I was at University of Queensland when he was doing his BSc honours in 19...
go to the pubs.
Okay, well from now on I won't be saying Professor Menger, it'll just be Paul. Paul was doing his honours degree in '89 when I was training, which tells you as much about me as him. He remained at the University of Queensland to research the neural and behavioural basis of electroreception in the platypus and the echidna, and was awarded his PhD on this topic in 1994. After completing his PhD, Paul was employed as a postdoc fellow at the University of California, Irvine, then at UC Davis, then at UCLA, and then at the Karolinska Institute in Stockholm in Sweden. He joined the School of Anatomical Sciences at Wits in 2002, was promoted to reader in 2006 and full professor in 2012. He holds a B1 rating from the NRF. He is on the editorial board of the Journal of Chemical Neuroanatomy and has published extensively. In March '93, while Paul was still doing his PhD and he was probably writing it up at the time, I participated in a meeting on biology and culture, nature and brain. At one point, one of the participants spoke lyrically of the Drosophila, the fruit fly. She was, she said, very fond of the fruit fly as a neurobiological model for vertebrate research, including for humans. I spent some time, whenever I was bored with the conversation, imagining doing research on Drosophila brain, teeny tiny brains, right? Fruit flies do have an advantage apparently in proliferating in lab conditions, of course. Large mammals do not reproduce so easily or quickly. But while fly neurobiology has pioneered various fields of neurobiology, including vertebrate neurobiology, flies are obviously not suited to all studied issues for vertebrates. And in this context, we work with the vertebrates that interest us most. Paul's interest is in African and other mammals and in the evolution of brain and behaviour, neuroethology, in investigating how brains change and comparing and contrasting brain morphology over time and across species. He has worked with very small mammals, such as mice, but in particular he has been drawn to charismatic megafauna, elephants, whales and dolphins, seals and camels, perhaps humans. His work includes his controversial, he has worked with humans on questioning whether we are charismatic megafauna or just. His work includes his controversial hypothesis on the development of the cetacean brain, that is of whales and dolphins, where he proposes a thermogenetic rather than an intellect basis to evolution of brains. With colleagues, Paul has also been studying sleep in free-roaming mammals, and he uses sleep as one of the key behaviours that can be related to the evolution of the structure of the brain. Here there is a link between the brains of large mammals like elephants and that of the Drosophila, since the Drosophila has also been studied in relation to sleep, physiological properties of sleep that are shared between Drosophila and vertebrates, opening up interesting questions about size and function. Paul established the first major mammalian brain bank in the Southern Hemisphere. There are a number of such banks in the United States, including the Comparative Mammalian Brain Collection at Michigan State U. But the one that Paul established is extraordinary in its scope, with specimens from over 150 mammalian species, making it one of the most diverse banks that can be used with modern neuroanatomical methods. Paul's studies provide numerous novel understandings of brain and behaviour in mammals, and his work is building a fundamental understanding of the processes of brain evolution and of how these relate to behaviour in mammals. I leave it to him to speak further to this. Paul, thank you.
Okay, so what I'm going to talk to you about today is what we've been doing in the lab. It's not just me, I work with a lot of different students and postdocs and collaborators. But this is the work that I like to drive, and it's understanding the evolution of large brains. And so what I want to go through is static. How do you actually, if I go like that, is that much better? Okay, I don't get static shock there. What I want to talk about is how we define scientifically what a large brain is. The fruit fly has a small brain, a human has a large brain, but does a monkey have a large brain? In comparison to a fruit fly, it does. So how can we say what a large brain is scientifically, using a real basis for that? And defining which species actually have large brains once we have that definition. To show that there are several evolutions of large brains in mammals and that these all follow independent evolutionary trajectories. And to show that, for the most part, a longitudinal body mass is the major factor in evolving a large brain. Nothing to do with intelligence. Okay, so I'm going to try to avoid as much as possible a whole idea of intelligence today. The next thing I want to show is that there is a specific metabolic adaptation that is the key for evolving a large brain. This is new and unpublished work that we have been doing, and some of the stuff we only found a week or so ago. And then to show that this supposed need for greater intelligence is not a factor in the evolution of large brain size. The human brain, the whale brain, the elephant brain, the camels and the seals, none of these brains evolved their large size for intelligence. Okay, so that's what I really want to get across through this talk. For the most part, the mass of the human brain is associated with scaling of body mass, going from a negative allometry to a positive allometry. There's two possible adaptive events, the origin of primates and at the origin of hominids. These changes may be positively selected changes. They may be adaptations, or they may just be neutral changes, things that happen that then show a change later on. So bipedalism is a great example of this. It may have led to an altered scaling of the brain-body relationship, but at first that might have been neutral. And I want to show in the next slide why I think this is neutral. So can we say that size alone accounts for the cognitive complexity of modern humans? To do that, we have to actually start looking at the building blocks of the brain. These are the neurons. So human behavior is more complex due to an increased complexity at the level of the neuron. We have a greater number of more complex units that are found in any other mammal. That's a very big difference. The neurons are more complex because of increased brain size, and brain size increases in parallel with increased body size, and at the origin of hominids, a change from a negative allometry to a positive allometry. Those three things put together help us understand human brain evolution and what it means for human brain evolution. So the majority of human brain evolution and our resultant behavioral complexity can be explained by allometric scaling laws of form and phylogenetic constraints. We're complex because we descended from primates. That's the main reason that we're complex. And primates have these allometric scaling laws and phylogenetic constraints written into their brains, into their genes, I suppose you can say. We don't need to have adaptationist narratives. We don't need to trade off gut size. We don't need to have fat babies and all these different things. The only time we need to actually invoke any adaptationist thinking is at the two specific events, the origin of primates and then at the origin of hominids. Other than that, there's no need to resort to complex and sometimes very convoluted ideas regarding human brain evolution. My answer to this question is no. I don't think intelligence was selected for in human brain evolution. I think it just kind of happened. All right? So that's humans. Let's go on to elephants now. So I'm going to change track a few times during the talk. So we look at elephant brain evolution. This is a nice picture I managed to take in the Kruger Park before we had to drive away very fast. All right, let's go on to the group that I'm infamous for, cetaceans. And I picked this picture particularly because of these little guys here, which are photoshopped in, by the way. Lots of people think whales and dolphins are second to humans in intelligence. So what happened in cetacean brain evolution? A few things happened. There was a dramatic increase in relative brain size and proportions of the brain. This was then followed by stasis. There was a change in the scaling relationship between the body and the brain. The negative allometry became even shallower, so that every doubling in body size in the cetacean only leads to about a 1.1 to 1.15 increase in brain size. There was a loss of the previously warm, nutrient-rich tethys C, and there's a cooling of global oceanic temperatures. So if we look at million years before present, so here's the Archaeoceti. They branched to give the Mystaceti and the Adulaceti, which is the modern cetacean fauna, and here we see a massive drop in the deep ocean temperatures. And this coincided with India crashing into Asia, Africa coming much closer to Europe, and North and South America coming together, and the Tethys Sea being wiped out. The whole globe cooled down dramatically. Now, this drop was about 6 degrees in deep ocean temperature. A lot of people say, well, 6 degrees, it's not that much. But remember, the temperatures they're living in are around 15, 16 degrees normally anyway. So I defy any of you to stand naked in 10-degree water for more than 10 minutes. I don't think anyone could do that, right? It wouldn't be so good. So to me, this is a very, very strong selection pressure. And this is where I developed a hypothesis that when they lost the Tethys C, which was warm and nutrient-rich and shallow, the oceans became cooler, that this change in temperature was the driving force behind evolution of large brains in cetaceans. And it also changed the way that their brains scale. So the cetacean brain enlargement as a response to combat heat loss in water. That's the hypothesis. So now, when I came up with that idea, then I have to prove it, of course. So, why do large brains evolve? The uncoupling proteins appear to be a very distinct metabolic key that unlocks and permits the evolution of large brains. The large brains don't evolve for intelligence, but for other reasons. The majority of brain size evolution can be explained by imperatives of allometric scaling, and we see that in human, elephant, pinnipeds, camels, although they're different trajectories, or in response to allometry and a specific selection pressure, which is the thermal selection pressure in cetaceans. So there's no reason to think that large brains evolved for intellectual capacity. I think that just came along afterwards in some lineages, but not in all lineages. And that we can actually go to a much more simple explanation in that increases in body size with one metabolic key allowing for large brains to evolve being the real answer as to why large brains came around. I want to thank all the students and collaborators, past and present. They all know how much work they've done and how much help they've been to me and how much they mean to me. Thank you very much.
I'd just like to make a comment on not only this work, but your work in general and how it's more than just quenches our academic interest and curiosity, but contributes to a field and contributes to our basic understanding of brain structure and function. That's not only for our understanding, but also applies to clinical translation and maybe explains why 80% of translational research from animal models to human models doesn't work, is because there's so much that we don't understand what the differences between rodent brains, primate brains, and mammalian brains in general. So your work is extremely valuable. Thanks, Prof.
Professor Soames is the Director of Neuropsychology from UCT. Unfortunately, Mark also seems to have brought some of the Cape Winter with him. We were beginning to enjoy the jasmine blossom and some green on the tree and on the trees in this parky area of Johannesburg. But I'm sure today's talk will amply reward our efforts on this chilly day. Professor Soames is, as I say, Director of Neuropsychology at the University of Cape Town and holds many prestigious positions within the global psychoanalytic and neuropsychoanalytic communities. He's President of the South African Psychoanalytical Association, a member of the British Psychoanalytical Association, and an honorary member of the New York Psychoanalytic Society. He is Research Chair of the International Psychoanalytical Association, Director of the Science Department of the American Psychoanalytic Association, and Co-Chair of the International Neuropsychoanalysis Society. He was awarded the Sigourney Prize for contributions to psychoanalysis in 2012. Professor Soames is a prolific and highly respected scholar. He's published more than 350 papers in both neuroscientific and psychoanalytic journals, and 5 books, including The Brain and the Inner World, 2002, which is a bestseller translated into 12 languages. His selected writings were recently published as The Feeling Brain in 2015. I've just got that on Kindle. I was very delighted to find it there. As if that were not enough, he's also the editor of the forthcoming revised standard edition of the complete psychological works of Sigmund Freud and the complete neuroscientific works of Sigmund Freud. So once again, I would like to say that it gives me great pleasure to welcome and invite Professor Mark Soames to speak to us on the neural mechanisms of dreaming.
So, thank you. It's great to be back at my old university. So you heard that I have some connection with this chap on the screen. And the reason I have him up there is because although humanity has been interested in dreams for centuries, it was, in a sense, Sigmund Freud who first tried to bring the matter of dreams, what they were about, what they're for, into science. Now, that was in the late 1800s. Freud's famous book, The Interpretation of Dreams, was published in 1899, although on the title page it says 1900. It's obviously trying to make it look modern. And in that book, he sets out a model of how dreams work, which I'll tell you about in a moment. But more important was the method upon which he based that model. The method was nothing more than asking people to say everything that came into their heads in relation to every element in the dream that they remembered from, say, the night before. This was the free association method. So, according to Freud, if you do that, and if you freely do allow everything that comes into your head to be put into words, then these streams of associative thoughts all connect up in an unexpected way and reveal, says Freud, a sort of underlying structure to the apparently meaningless dream. And according to Freud, this underlying meaningful entity that you can discern if you follow his method is that every dream is an attempt to fulfill a heartfelt, basic wish. You will all have noticed that in your own dreams you don't fulfill heartfelt, basic wishes. In fact, most dreams are quite hollow things. And Freud said, well, that's because it gets disguised and distorted. Because if you were to see what you really want, it might distress you, and this might wake you up. So this is why it's called interpreting the dream. The dream, on the face of it, is not the actual thought process. The actual thought process is behind the scenes and has to be inferred. Now, you can see why not everybody thought this was a convincing basis upon which to build a theory of dreaming, but that's what Freud did, and that's why I say it was, in a sense, Freud who brought it into science. At least he thought he was doing science. Karl Popper, who sort of is the authority more than any other recognized for deciding what is and what is not science, differed from Freud on that point. He said famously that psychoanalysis is pseudoscience. That's the word he used, by which he meant it looks like science. It has all the trappings of science, but actually it isn't science. And shibboleth for Popper is, does it give rise to testable and falsifiable predictions? So in the case of dreams, as I just told you, Freud says, well, the dream doesn't look as if it's fulfilling a wish, but if you follow my method, you can discern, you can infer that actually there's a wish there. And Popper correctly points out, well, how the hell do you falsify that? If you say there's a wish there, then how can I show you there isn't a wish there? There's no prediction that can be tested and found to be false. So it's on that basis that he said this is a pseudoscience. Leaving that aside, let me come back to what Freud claimed. He claimed, as I said in that book, he drew up, he made a model of what he thinks is going on in the mind during sleep, and the model works like this. He says that the mind can be divided into roughly two parts. The one part registers the outside world, and this he called the ego, and the other part registers the inside world of the subject, and this he called the id. And the id sort of registers therefore the state of the body and all of your basic needs and urges and wishes and wants. When you go to sleep, says Freud, the ego switches off. So you close your eyes, switch off your thoughts and externally reality orientated bits and pieces, but you can't switch off your id, says Freud, because it's regulating the vital needs of the organism. So during sleep, says Freud, the balance of power shifts, whereas normally the ego is inhibiting with all of the reality constraints, it's inhibiting the id, that is to say all these basic urges. During sleep, that inhibition is lifted when the ego goes to sleep, and then the id makes hay while the sun shines. Now, please notice there's a curious problem with this theory, which is that, well, if all of your inhibitions are lifted while you're sleeping and all of your urges, wants, and wishes come, popping out, then how the hell do you stay asleep? And Freud said that's why you dream. He says that the dream is an attempt to in an hallucinatory, delusional way, to kid you into thinking that your wishes and wants and desires are being fulfilled. That's what Freud said. So the dream, the function of the dream, according to Freud, is paradoxically to protect sleep. It enables you to stay asleep. Okay. Now, it's not only Popper who found this all implausible. Many people found it all to be implausible, but some did not. and they were called psychoanalysts. And this dream theory ended up becoming a sort of foundation stone for the whole of psychoanalytic theory. Because Freud, having built this model of how the mind works during sleep, in order to explain his findings about dreams, he then went on to expand on that model to build a theory of how the mind in general works, starting with the not irrational point that dreams are a form of madness. You know, if we can understand the psychotic process of dreams, then perhaps this gives us some insight into other mechanisms underpinning not only psychosis but psychopathology as a whole, and and so on and so on. Now, we tend to forget this, but that theory, the psychoanalytic theory, was very authoritative at one time in psychiatry. In the 1940s and 50s and 60s, you really could not get a tenured position in a psychiatry department in America if you were not a psychoanalyst. It was considered like a necessary basic qualification. To be a psychiatrist is you have to train in psychoanalysis. And America, was then also the center of the world. So American psychiatry was entirely dominated by psychoanalysis, and the knock-on effect was, in a sense, world psychiatry was to a large extent dominated by psychoanalysis. And as I've told you, the psychoanalytical model of the mind started with the theory of dreams. And so this theory, a lot hangs on it, and a lot hung on it in those days. So it was, I'm sure, something of an embarrassment to psychiatry that it was so dominated by a theory which ultimately starts with a model about dreams, all of which rests upon this method, which I've already explicated to you, which is, hardly reassuringly rigorous. So they were delighted when in the early 1950s, something called REM sleep was discovered. It sliced the frontal part of the brain away, slowly slicing deeper and deeper down the brain. In other words, he started at the top end of the neuroaxis and sliced progressively deeply into the brain to see at what level do I need to make the cut for REM sleep to stop. And he eventually sliced the entire forebrain off. In other words, leaving the hapless cat with a brain stem only. And to perhaps his surprise, the REM sleep persisted unabated. So that proved that the forebrain, that is to say, the organ of the mind, is not needed to generate REM sleep. And in fact, Jouvet cut all the way down here, down here, it was only when he got to the level of the pons that REM started to falter and was in fact obliterated. Now, here's the spinal cord, here's the medulla oblongata, here's the pons. It's pretty base. This is dreams are generated at a very low level in the neuraxis. This led Jouvet to come to the not unreasonable conclusion that Freud must have had it horribly wrong, because clearly dreams are not driven by anything mental. Not only, this part of the brain, it's regulating the sorts of things that I was just talking to you about, things like breathing and heartbeat and body temperature and basic arousal states. There's really very little thinking about your mother that goes on in your pons. And then you have to also remember that it happens automatically every 90 minutes. So no matter what kind of day you had, pretty much a dead certainty that you're going to have REM sleep every 90 minutes on average every night. So Jouvet came to that conclusion, and then his student, Alan Hobson, carried on the quest to work out in more detail what it is that generates dreams. And what Hobson found, focusing on the pons, was that there's a group of cells here in the mesopontine tegmentum. These are cholinergic cells. I don't know what audience I'm speaking to, by the way. Sorry, I'm assuming you're not all neuroscientists. So these are cholinergic cells, which means that at their terminals, which broadcast very widely in the forebrain, at the synapses, they release a chemical called acetylcholine, a neurotransmitter called acetylcholine. That's what cholinergic means. So what we found was that these are the cells that switch REM sleep on. They fire in non-REM sleep, they fire at a slow rate, pop, pop, pop. And then just before you go into REM sleep, the rate increases. And that's how they fire in REM. Conversely, two other cell groups in the pons, the nucleus locus ceruleus complex and the dorsal raphe nucleus, which release neurotransmitters called noradrenaline and serotonin, respectively, do the opposite. So when you're in non-REM sleep, they're firing at a rapid rate, and as you go into REM sleep, their rate goes down as the cholinergic rate goes up. So, that's what happens. That's called the reciprocal interaction model of Hobson, published it in 75. And you will notice there's a simple switch. I mean, that's basically what he showed, that there's a switch, a little on-off, in your pons, and it goes on and off automatically every 90 minutes. That's what generates dreams. On the basis of this elegant series of experiments, by the way, it wasn't just lesion studies that he did, single-cell recordings, he did micro-injections of acetylcholine into the mesopontine tegmentum and switched on REM, so on. It really was a done deal after Hobson. There was no question as to what it is that generates REM sleep. And Hobson then published a paper in the American Journal of Psychiatry, not a physiological paper, but rather a neuropsychological paper, I suppose is what one should call it, in which he spelled out a model that he called the activation synthesis model of dreaming. And it's a very simple model, which is a good thing. He said the mesopontine tegmental cholinergic cells activate the forebrain. And while they're activating it, it is demodulated because the serotonin and the noradrenaline are down, the spiky acetylcholine is up. So you've got a switched on brain that's demodulated. And so, your poor brain, it's doing stuff. With this random activation, as I said, the cholinergic projections are very diffuse and widespread in the forebrain. So the whole forebrain is just switched on like a Christmas tree by intrinsically, essentially, fundamentally meaningless signals. And I emphasize that because what Hobson was showing is that dreaming is a mindless state. It cannot possibly be motivated. It cannot possibly be the result of wishes and thoughts, and let alone all these gymnastics about censorship and disguise and all of that. It's just a switch where the forebrain is activated and demodulated. The forebrain, as I said, the organ of the mind, has all of your mental representations in it. So, when you switch on the forebrain, you're switching on visual images, auditory images, memories, volitions, thoughts, feelings, and so the brain now has a whole lot of visual things going on, auditory things going on, somatosensory things going on, feelings, memories, blah blah. What does the poor forebrain do? It's according to Hobson, well, it just joins all the dots. It synthesizes all of these representations into an episode of an experience. And to quote Hobson, he said, the forebrain makes the best of a bad job. Okay. Again, I must emphasize that it is an intrinsically meaningless mental state. Normally the forebrain, if you see something, it's because there's something there. Your brain is responding to something that your retina is picking up about the world. If you're thinking something, it's because there was something else that led you to think that thing. There's a causal, a meaningful structure to cognition, which does not apply to this state, which is just switching on the lights randomly and joining the dots. Now, Hobson made this important point. He said, of course you can come afterwards and find meaning in the dream. It doesn't mean that it is inherently meaningful. In other words, it is not caused by psychological, meaningful processes. He made the, I think, good analogy that with the Rorschach test. You know, there's an ink blot, and you show everyone the ink blot, and you say, what does this mean to you? And they'd say, ooh, it's a vagina, you know. And you say, oh, really? You know, that says something about you. But remember, it isn't a vagina. It's an ink blot. Okay, so the ink blot is inherently meaningless. You can project meaning onto it ex post facto, and Hobson says that's what psychoanalysts do, and their patients. You know, so it's no surprise you find meaning in dreams. You can find meaning in any bloody thing. Looking at the clouds, you can say, "Ooh, it looks like a donkey." You know, but it isn't a donkey. It's a cloud, you know, which is not trying to represent anything in itself. You get it? Okay, that was Hobson. Then, in this very hallowed institution, a Yapi came along. That was me. And I was a neuropsychologist. What am I doing here? And Hobson, you know, all respect to him, you know, to say that the forebrain's job is to synthesize is a little bit of a simplification from a neuropsychological point of view. It's like, what do you mean the forebrain joins things together, you know, synthesizes them? Different parts of the forebrain do different things. We knew that by the 80s, which was when I was here, and so I came up with the idea, not exactly a brilliant idea, that if you take a patient who's got damage to this part of the forebrain, the visual part, maybe they'll have long-visual dreams. And if they have damage to this part of the forebrain, Broca's area, the language production area, maybe they won't speak in their dreams. You know, if they have a lesion here in the motor strip, maybe they will be hemiparetic in their dreams. In fact, that's what you would expect on Hobson's model. You know, the forebrain, all the representations are being randomly activated and joined together. If some of those representations are selectively missing, those can't be part of the synthesis. Do you get it? So I said, okay, let's test this. So I took human beings. Very important that I took human beings. By the way, I didn't cause any damage to anyone, so it took me a long time. I took 361 human beings who had not caused by me, but rather by God, damage to specific parts of their brain, and I collected them together in groups, so that I had a group who had damage there, and a group who had damage there, and a group who had damage there, and so on, all over the place. And why they were humans was because I needed to get access to their dream content. You know, so as much as cats and dogs and rats and mice have REM sleep, which by the look of things is their physiological manifestation of their dreaming, we can't ever get access to their dreams. Very important. I'll come back to that. But I had people who could speak, and so I asked them, has anything happened to your dreams? And they told me, slowly but surely, I started to see commonalities. That all the patients with lesions here had this thing, and all the patients with lesions there had that thing in their dream content. We then woke these patients up in REM sleep when they have dreams, when you can have the most direct access to the dreams, and got dream reports to see whether their bedside morning recall was consistent with what you could find in the sleep laboratory. And on the basis of that study, which, as I said, took a long time because it takes a long time to get so many patients with the correct sort of lesions, eventually I was able to come to some conclusions, which I will now show you. Each of these lesion sites that I'm showing you here led to a reliable, reproducible change, predictable change in the content of dreams. Now, I'm not going to tell you everything that I found because it will take me too long. I'm going to focus only on the most dramatic findings and, as it happens, the most unexpected findings. Here is the first thing that I found. Patients with damage here that is to say in the parietal lobe of either hemisphere, they stop dreaming completely. In particular, in the inferior parietal lobule, the supramarginal gyrus. In particular, patients with damage there stop dreaming completely, but they still have REM sleep. You wake them up in REM sleep, they have no dreams to report. That was the first dramatic finding, is that there's a lesion site in the brain which leads to loss of dreaming in toto. If they have damage to both frontal lobes, in the ventromedial, that's the low, deep quadrant, in the white matter, damage there on both sides leads also to loss of dreaming, and that's not at all obvious why that should be the case, but it is the case. Now, the third group that I want to show you is this group here, the light blue area over there. That is, so the second group, they have white matter lesions there. Okay. Now, the group that I'll show you third, they have lesions there. Remember that area, mesopontine tegmentum. The surprise was that these patients, well, what was not surprising is that they lose REM sleep. Well, that's, same as you find in cats and the same as you find in rats. You damage the mesopontine tegmentum, REM stops. But the surprise was that dreaming did not stop. Now, those of you who are neuropsychologists will know that what I've just described is called a double dissociation of function. That is the gold standard in neuropsychology. If you're going to say that a brain region performs a function, then you've got to show that the removal of that region leads to a loss of that function. But double dissociation shows even more. It says damage here leads to loss of dreaming but not loss of REM sleep. Damage here leads to loss of REM sleep but not loss of dreaming. That means dreaming and REM sleep are two different things. They are doubly dissociable. They cannot possibly be the same thing. Do you get it? So now my focus shifted to this area. As I told you, it's no surprise that parietal lesions lead to loss of dreaming, but this deep bifrontal white matter lesion leading to loss of dreaming was a big surprise. So the question became, what is it? What's going on in this part of the brain? What function is being performed by this part of the brain, which is obviously so essential to dreams, because when that function is gone, dreams are gone. Now, that part of the brain is spaghetti junction, this white matter from everywhere to everywhere. So it was not obvious to me at all, what was the critical bit that led to the loss of dreaming. But looking at these scans led me to an hypothesis. This scan reminds you of something if you're old enough, and that is, this is where they used to do the modified prefrontal leucotomy. It's exactly where they produced the lesion in fact, thousands of psychotic patients in the 40s and the 50s. Why did they produce? Well, they used to cut the whole frontal lobe off. It was called frontal lobotomy. And this helped in the sense that the patients got dramatically better in terms of their hallucinations and delusions. But they got dramatically worse in terms of no longer having frontal lobes. And also it's a big operation. So there was lots of not only morbidity, but also mortality. Wanted to see, did any of these psychiatrists who ordered this operation, did any of them ask the patients about their dreams after the operation? And to my amazement, they did. When I say to my amazement, it's because somehow, the sleep scientists didn't read the psychiatric or psychosurgical literature and vice versa. Had they read each other's journals, they would have seen there's a big mistake being made here, because it was reported in hundreds of cases in the 1950s that operation, the modified prefrontal leucotomy, leads to, number one, dramatic reduction in hallucinations and delusions. Number two, loss of motivation. Number three, loss of dreams. And Schindler went so far as to say, if the patient continues to dream, it's a bad prognostic sign. It means the operation hasn't worked. And that made me think, Well, that makes sense, because if you can generate a dream, you can generate an hallucination and a delusion, because that's what dreams are. So that's what put me onto the hypothesis that I'm going to tell you now. So this operation was superseded by what was then called major tranquilizers. That is to say, antipsychotic drugs. It's because there's a fiber pathway coursing through exactly there that is a dopaminergic pathway that is blockaded by antipsychotic drugs. So my hypothesis was that's the pathway that's necessary for dreams. So it's from BTA to nucleus accumbens. I don't know if any of you know what happens if you give anticholinergics to dreams, but now we know because we did the critical experiment, and what it shows is that it increases dreams. And with antipsychotics, it suppresses dreams. Why should this system be so important for dreams? What does it tell us about what dreams are? You know, that's the value of neuropsychology, is you find out which brain region is important for a mental function, so that you can learn something new about that mental function. And so my prediction was the non-dreamers will have worse sleep than the dreamers. And after that debate, our colleagues voted 2-1 in favor of the motion that Freudian dream theory still has some scientific validity, in 2006. And as I said, that's before the sleep protection study came out. So we really do owe Freud an apology. It does not mean that Freud was right about everything about dreams. I personally do not believe a lot of what Freud said about dreams. But I do think that we owe him an apology, that dreams are motivated mental states, that there's every reason to believe that this person, what's going on in their minds matters to them, and it's heartfelt, and it's emotional, and it's motivated, and it's wishful, and it's desire-driven. Everything else we can leave to the discussion. That's the brain mechanisms of dreaming. Thank you very much.
So it's my turn to do the introductions, and it's really a great pleasure for me to welcome and introduce Dr. Samantha Brooks. She's a chartered member of the British Psychological Society, and she's currently a senior lecturer in the Department of Psychiatry at the University of Cape Town. As you'll see, Dr. Brooks's research specializes in the neural mechanism of impulse control in a range of psychiatric conditions, such as addiction and eating disorders. Previously, she completed her postdoctoral fellowship at Uppsala University in Sweden, where she continues to collaborate on projects examining brain processes underlying eating disorders. She gained her PhD at the Institute of Psychiatry, King's College London, where she learned clinical neuroimaging techniques such as structural and functional magnetic resonance imaging. Dr. Brooks has published extensively with over 60 papers and various book chapters, and she continues to present at international conferences. She hopes to improve our understanding of the brain processes involved in cognitive control or willpower, so that people with impulse control problems can be trained to improve their self-control and ultimately lead more fulfilling lives. Without further ado, over to you, Dr. Brooks. Thank you.
I'm not going to give 3 outlines for my talk, but these are very small snippets, so little bite sizes for you. So I'm going to talk a little bit about impulse control at opposing extremes. I'm going to talk a little bit about the neuroscience of impulse control, and then I'm going to bring in something that I haven't really done a lot of in previous talks. This is new, so kind of hot off the press for you guys. I'm going to talk a little bit about the Bayesian brain and how that relates to impulse control, because my desire is to unpack how we can achieve cognitive control, what the brain does. So back in the IOP Institute of Psychiatry in London, I was very keen to understand cognitive control, but it wasn't quite clear to me how the brain does it. And Carl Christen's work on the Bayesian brain, I think, is very exciting and helps us to go one step further. And then I'm going to try and link that to translational neuroscience and how we at UCT have developed a new adjunct to treatment to try and improve impulse control in various disorders, including substance use disorder and ADHD. Then we're going to talk about some data. Sandra told me I must bring some new data, so I've done that. And some very, very new data that I was busy finishing on Monday, ready for you guys, so I want to impress you. And then some unanswered questions. Hopefully these are questions that will inspire further research in you guys, and some conclusions. So, conclusions then. So at the very beginning of the talk, I said, can we learn from anorexic brain about how to sustain conscious veto? And I think we can. And why can't impulsive people do that? I think we've probably got a lot closer to answering that question, and keeping in mind this Swedish concept of lagom, just enough. And again, not suppressing your passions or your desires, but holding on to them and not getting lost in them, keeping your head. So these are just final take-home messages. And the passive stimulations are non-consciously activated, perhaps half a second before consciousness. So that's interesting to think about. And can people with anorexia, or those people with anorexia, seem to exercise complex ruminations, which we can also call epistemic foraging, that acts as conscious veto of appetite. So next time you want to control yourself, you're eating or whatever it is, think of something you can ruminate on, or really forage in your environment to keep your mind active, and that will prevent you from thinking about the thing that you're trying not to think about. Repetitive working memory supports epistemic foraging that updates predictions about the future, the basic brain processes, and do look at Carl Friston's work, it's fascinating. And neuroplasticity related to epistemic foraging might help to control behaviour and compulsions. And yeah, don't forget to repeat working memory training fosters neuroplasticity. And the last slide, forgive me for being a bit cheesy, but I've got back into poetry writing. I used to love writing poetry when I was younger. And so I've written a little poem alongside my collaborators that you can read if you want to, about impulse control, and I hope you like it. I actually also put this at the end, but I think I'll... That's just my little crush there. Thank you for listening.
It is indeed the talk show here on SFM, and we bring you the Neuroscience for Society lecture at the Nelson Mandela Children's Hospital in Parktown, Johannesburg. This one is the final part of the Brain Matters initiative, and it's presented by Professor Morten L. Kringelbach. I must give you quickly a bit of background on him. He comes all the way from Oxford University. In fact, he runs the Hedonia Research Group based at the Universities of Oxford and Aarhus. His prize-winning research uses neuroimaging and whole brain computational models of, for example, infants, taste, sex, drugs, and music to find ways to increase well-being. I was going to use that word. What is it? Say it when you're done.
Eudaimonia.
Eudaimonia. You learn something new every day. He's published 14 books and over 300 scientific papers and chapters and other articles, and his research features regularly in newspapers, magazines, radio, and all over the media. He's a fellow of the Queen's College, Oxford, of the Association of Psychological Science, and is on the advisory board of Scientific American and a board member of the world's first Empathy Museum. He gives us his lecture titled The Parental Brain, New Insights from Brain Imaging. Ladies and gentlemen, please give him a warm round of applause.
Wow, that's all I can say really. It's an amazing honor to be here. I've had a long-standing collaboration with Linda. It's wonderful to be here in this very special place where, as you said, Nelson Mandela really did care about children. So it's wonderful to see that you've built such a fantastic hospital of the likes that I've not seen anywhere really. So what is it that we're really interested in today? On a day like this, when I had sort of hoped to come to summer, and instead I seem to have brought the weather with me. So the rains, I think I've no better thing than to go on YouTube and search for 4 laughing babies. And if you do that, you get something like this.
That don't make me laugh, my friend.
Aren't they cute? And it's just contagious. And people go up to it. 4 of them, right? Imagine what it's like when they're crying. You never get tired of it, and it's perfect for the kind of weather you normally get in the heat. But I understand it's usually better there. So, what is it about life? What is it about life, growing up in a seat like this, babysitting in a half-full tub and still feeling that the world is a wonderful place? What is it about growing up with the right kind of parents? What is it about growing up with no parents in orphanages, like in this image from San Sebastian Salgado from Latin America? What is it like? Orphanages, of course, should be banned. There's no good idea of that. Really what we need is caregiving. And what we tend to forget is that children are vulnerable. They're basically not fully formed. We have to take care of them, and the extended human childhood requires extensive nurturing. And if there are long-term problems, and again, the listeners will have heard about this before, there's an incredible toll being taken by parental postnatal depression. And even if there's something wrong on the part of the baby with a cleft, that changes things and makes it a lot harder to care for that and give it the right kind of caregiving. So what I want to take you today through is basically talk to you about the kind of research we've done. But I also have to show you this image of the kinds of problems that are in low and middle income countries around the world. You can see that places like Malawi, there are mothers there, 30% of mothers in some townships. Same, of course, in parts of South Africa. So we really need to use the neuroscience to basically make a difference in the world. And that's why I've come all this way to talk about the neuroscience, so that together we can find potential solutions to that. And as this particular graph shows, it's important to invest in the early years. Hickman, who got the Nobel Prize in economics, showed that if you start very early, you get much more bang for your bucks. Solve the problems early, and you don't have to spend a lot of money later on. So we need to look inside the brain. In this image you can see a mother cradling her daughter. This is actually quite a well-known researcher from MIT with her daughter in Ghana, Rebecca Sachs. And so eventually when I then wanted to study the brain and use those new scanners that have come online, I moved to Oxford, as this particular image will show you, and I wrote a thesis called The Functional Neuroanatomy of Emotions. And that was a very interesting time. And I learned a lot about the brain, some of which I'm now going to tell you about. Because as we're looking at each other, the only part of the brain that we can actually see with the naked eye is exactly the eye, is the iris. Here's a photo of a young lady's eye. This is my good friend Anna Catherine, who was a sculptress. This is her niece. This is her eye, and this is her mother's eye. And as you look into it, what is it that you see? Because you see, one of the things that's important about us humans, and in fact any of the kind of species on this earth, is that we have templates. We have things that we kind of try to see. So what I'm showing you here is an image, black and white image of something that I don't think anybody really can see what it is. And yet all I need to do is to show you the full photograph of the actual two little girls, my two daughters when they were younger, sitting there, and you can't help yourself, now that you've got the template, to see them there. So we're prediction machines. We're very good at finding templates and trying to predict from those templates what's going to happen. And we are very interested in this part of the brain called the orbitofrontal cortex, because that's where all the pleasure is happening. Just over your eyeballs is one of the most important parts of what makes an emotional brain. Have a look at this one. And now before I do that, just have a look at this quote. Quid recipitur ad modum recipientis recipitur. I don't know how good your Latin is, but basically means that the content is shaped by the container. And in this case, if you think about the glass plate and the sand corns, have a look at this little video. You can see how different tones make different kind of patterns. And it's solely linked to the kind of vibrations that are on this particular plate. Now this is an organizing principle in nature, that different harmonics will give rise to different kinds of movements. And it's true of many different things, like for instance here for sound as well. In fact, this is the sound with different kinds of vibrations. You see how it gives us very beautiful different kind of patterns. If you change the container,
you get very different kinds of patterns as well. Here's a guitar, and you see how it is that those harmonics play in very different ways that then gives us these beautiful things called music. You can even start to basically look at the diffusion equations. You can start to think about how you get these harmonic patterns in space and time, and if you change the frequencies and the way they propagate through, say, acoustics, like I show you here, or quantum mechanics, like I show you here, or electromagnetism, you can see how it gives rise to different kinds of patterns. And even if you think about something which, of course, is dear to your heart here in South Africa in the new games, you know, giraffes, jaguars, zebras, if you look at how it is with different parameters, you spread these kind of things, you get the different kinds of patterns. This is exactly how the lipids go as patterns. And the big question, of course, is what happens then if you spread that within the brain, within the structure. And here I'm showing you the wiring of the brain, the human connectome. And so think about if you then spread different kinds of harmonics through this. This is the work of my good friends in Assessor, who's together with us have shown that you basically get these sort of multiple components, which is what is making up your brain activity. You can then start to build models of this. You can see how things propagate. And once you do that, and don't be frightened by the math here, you can basically build models that will replicate the kinds of activities you see. So that means suddenly I'm no longer constrained by the phonology. Suddenly you have a model that I can leash you and find out what parts of your brain are important for things like parental love. The first thing to realize is that as a parent we have certain possibilities, certain things that we have to look at. Immediately when they're very small, they have no other thing than basically cuteness. They become the main focus of our attention. And they really have to give us the tools to give us the right kind of responsiveness. After that, as they get a bit older and a little bit less cute, we have to provide them with emotional scaffolding, principally through warmth, consistent support, especially in a stressful situation, which helps a child maintain emotional regulation. And then as they get even older, we then start to have to give them the capacity to provide sensitive responsiveness in relation to the child's attachment and relevant need. And that, of course, is mostly about separations. So today I'm going to talk mostly about the first part. So what is it about babies that attracts us? The way they look, the way they sound, the way they smell. This is all work that I've done with Alan Stein, who I'll talk about a bit later. We start to look at what parts of the brains are active when you're feeling groovy. This is the brain when you are feeling pleasure. This is the brain when you're feeling groovy. So I give you what I call the eudaimonia of groove. And you all know what that means. It means human flourishing. It means the kind of things that we could use to interact with those babies. Make them dance, make them sleep. Use music as a way of interact that allows us to show us really what is the nature of love. But there's much that remains to be done, and I'm hoping to do that with you here. Here's a center that we've done in Denmark. Here's some Danish people being groovy. There's a book I've written called Emotion, Pleasure and Pain in the Brain. I also wrote a book called The Pleasure Center, a paint book, as you can see. And when you do that, people in Oxford look at you and they say, "What are you doing? That's science." And so I was pretty sure it was science, I have to say. So I wrote another book called Pleasures of the Brain, which is a sort of a magnum opus that when dropped on the third floor can kill a man or a woman. So if you really want to know about pleasure, I'd love to vote to ask, that's the book to go for. Also to remind us, I wrote a book on consumption, not tuberculosis, but what happens when we buy. And again, I'm not sure there's a lot of pleasure there, there's certainly a lot of obsession. And of course, when we think about the parental brain, that is really the one chance we have of really being changed. There are three major moments in our lives. When we're little, first 18 months, which is really when the thermostat of how much we can enjoy this life or not. And of course, very much linked to our caregivers. Then adolescence, when is when we like to learn the right kind of music. And then there's when we become parents. Parenthood changes us more than anything else. And what it shows us, I think, is really our capacity for love. And these little critters, with those kind of templates that we have in our brains, that, by the way, is one of the reasons why we breed cats and dogs to look like babies, is because that's what we like. This is really why we get excited about these things. But at the end of the day, it's about empathy, it's about the nature of love. And I'll just finish with one of my favorite poets, Derek Walcott, who says, "For every poet is always morning in the world. History a forgotten insomnia at night. History and elemental awe are always our early beginning, because the fate of poetry is to fall in love with the world in spite of history." Thank you.
Good afternoon, everyone, and welcome. Out of interest, how many people here are avid dog lovers? Put up your hand. Okay, the rest of you can leave. Well, welcome everyone. Thank you so much for coming. And I'd just like to say special thanks to Dr. Mohammed Safda for presenting on this fascinating talk on the effects of domestication on the canine brain. And on behalf of the Litz Cortex Club, I, Victoria Williams, would just like to thank the Emerging Diaspora for allowing us to be involved in this exciting talk and to collaborate. So thank you so much. Thank you. And Professor Paul Mayer is going to tell you a little bit more about Dr. Safda. Thank you.
So for those of you who don't know the Spock, I'm just going to call him Spock because that's what we know him as. I first met Spock 15 years ago, well maybe a little bit more than that now, when I first arrived at Wits. He was an honours student with an interest in paleoanthropology. Slowly I got him over to the dark side of neuroscience. He did his master's with me and then his PhD. Following his PhD, he had a short postdoctoral stint in Santa Barbara, then went to a very nice neuro lab in Washington DC with Professor Chet Sherwood, who's a friend of mine and also someone I continue to work with. And then got his own faculty position at Des Moines University in Iowa, where you are now tenured. He is now fully tenured and establishing his own lab there. Spock has a very eclectic range of interests. He had a very generalised educational background here at Wits and saw many different things. But I think that sort of started to crystallise into a very distinct research idea that he wants to talk about, that he wants to work on, and that's what he's going to talk about today. So I'm not going to say anything about what he's talking about, I'll let him do the talking. So please welcome Spock here for his talk.
Today's talk is going to be on domestication. I've been fascinated with this question over the last few years, and as Prof. Manka said, I've been a little bit of a generalist, trying to find my niche. But domestication is something that is of relevance and of interest to all of us, because you'll soon see as I talk through this that there are a suite of characteristics. One would define as the domestication syndrome, which in many ways we can see parallels with that in our human condition. So sometimes when I look at this from our perspective, it's not just about understanding the dog condition and the trajectory of the canid brain, but it's also a little bit about understanding the human condition and perhaps posing the question, have we self-domesticated? Okay, what are those characteristics that we perhaps share? So we're using essentially a convergent evolutionary lens to use the domesticated dog as a parallel to understanding the human neural systems involved in domestication. So I have a few objectives quickly. I'm going to introduce my laboratory's research focus in comparative anatomy, neuroanatomy. I'm talking to a largely favorable audience. A number of you are familiar with comparative neuroanatomy, but I'm not going to take it for granted. I want to emphasize why this is really important. I'm going to provide an overview of the neuroanatomical changes associated with domestication. I'm not the first person to work on this. I'm standing on the shoulders of giants who have worked on domestication. And there's been a bit of work which we are contributing to. And then also we're going to be looking at some preliminary work that we've been doing over the last few years, collecting data, collecting brains, and a whole range of canids, both in Des Moines, Iowa, and also with the help of Prof. Manga back here in South Africa, which is helping us to complete this picture of the evolutionary history of the canid brain. So, conclusions, let's look at this quickly. I'm going to try to let this video play in the background real quickly as I do that. There we go. Not much evidence for relative expansion of total cortical area or white matter and canids. However, there does seem to be some variation in the genu, particularly pointing to the frontal lobe. Domestic dogs have seemed to involve increased gyrification. So there is data for increased gyrification. This increased cortical folding, we argue, is a result of an expansion of a total pedal surface. And we've identified some 6 novel polymorphisms. And we're starting to look at the endocast data and using this endocast data in alignment with the extant species. Some of the more I would say, more distant goals of our series is to use the data and make it available to others. So what we've been doing the last few years is actually creating these three-dimensional reconstructions. I work with a colleague at Iowa State University. He teaches at a veterinary school, and we've been printing 3D models of some of these brains, of the canid brain, to show that internal anatomy. Not shown here as beautifully. Let me see if I can get that in play. Showing you, for instance, there you can see some of those subcortical structures. You see some of the subcortical structures in green. That's your hippocampus sitting here. There's your amygdala. There's the caudate sitting here, winding around. There's a little bit of the corpus callosum. Lovely columns of the fornix ending up in the mammary body. So again, helping not only researchers to kind of visualize a little bit of this, but hopefully students who are anatomy to visualize some of these subcortical structures. That's some of our work here. And of course, with the help of Prof. Manga, we actually busy with a project with Samson, who's in the back, Chengatai, who's one of our London students. We've been looking at African wildlife and creating digital MRI atlases, of these really studied species. Thank you very much.